Testing one. All right, everyone, how are you this evening? Yay, we've got a lot of people hanging around. We hope you want to come over and join our conversation. We're going to be talking about methods of decarbonization that we may not always think about, particularly in the residential and light commercial sectors. Now, all right, I know we're going to spend a lot of time on the commercial side.
You're going to say you better be talking about
we were talking about
okay, got it.
but I'm going to use it to highlight like my secret agenda as to what we're going to be doing in residential down the road, so that everyone knows that this is great stuff.
So it'll trickle from commercial to
right
residential. Got it. Okay,
exactly
fair enough. Okay.
All right. So if you don't mind, you guys mind introducing yourselves to the crowd?
Yeah. I'm Rob Tanner. I'm Director of Marketing for Applied Commercial Equipment, right, for Johnson Controls. And the topic of heat pumps, the three of us share a passion about that, right, as we think about ways to help decarbonize practically. Right?
Yeah, absolutely.
So, good.
Okay.
Yeah, and I'm John McCrae. I'm Area General Manager for Equipment in the Southeast.
Okay. All right. So let's start talking about solutions that we have for the industry and ways that we can look at maybe having existing systems and retrofitting them with new solutions, maybe even solutions we haven't even thought about. We spend so much time talking about the transitions of technology that's happened in heat pumps, particularly in the last 10 years. More so in the last couple of years, really.
Right.
And so the performance that we're seeing out of some of these new high performance, very low ambient operating heat pumps has applications in so many sectors of our industry.
It does.
Yeah.
And so when we think about buildings, commercial buildings, I'll start there, where we have the opportunity to take advantage of, and I'll just talk air to water for a moment, right? Because we're finding through technology ways to get more and more of that heat from the ambient air to a usable heat to heat the space, right? But I think the other part to think about is that's air to water. There's the water to water piece, which is typically thought of more for commercial applications. But if you have a unit that can do both, where you can function as air to water, but also do water to water.
Oh, wow.
Well, think about the applications in commercial buildings where we have simultaneous heating and cooling needs.
All over the place.
Everywhere,
You
right?
betcha.
And if I can take that energy that I need to cool somewhere, I need to heat somewhere else, and if I can just move it, that's what a water to water heat pump allows me to do, right? I can get, as John always likes to say, we could take one electrical input and I get two outputs. I get cooling for a part of the building that needs that. I get heating for other parts of the building that need that.
Yeah.
And now, you know COPs, you're comfortable with coefficients of performance, 6 to 8 versus 3 to 4.
Yeah.
That's a lot.
You betcha.
Right.
Well, and if you think about like the whole principle behind what all of us do, whether we are in the HVAC or the R part, we're in the business of moving heat. And
that's it.
And so we can't limit ourselves on how we move heat.
Right.
We need to be able to think from a broad perspective, what are the means and the ways of moving heat? Well, when we start thinking about it from a water perspective instead of just a refrigerant perspective,
correct.
Boy, we can move heat anywhere that we need it.
Absolutely we can. And we got all the flexibility to do that. So
Sure.
Yeah, and so if you take a subset of the existing buildings and look specifically at the condensing boiler and air-cooled chillers installations, right? That's where the air source heat pumps, as in the air-to-water heat pumps, are really the best fit.
Yeah.
And part of that is the design hot water temperature with condensing boilers is usually quite a bit lower than with traditional boilers. In older buildings, a lot of times it's 180.
You betcha.
You really can't touch that with an air source heat pump, air to water. But 140, 130, you're starting to get in the neighborhood of what's possible with air to water. And it's really interesting that there's quite a bit of difference between different product lines. At a given ambient temperature, one air source heat pump product will only be able to make 110 or 120 degrees, and another one might be able to make 130.
Oh, okay.
So the YMAE product that we have on display over there, it'll do 140 at 25 degrees, but what's even more impressive, I think, is it'll do 130 degrees at 0 degrees Fahrenheit.
That's a significant amount of heat. I mean, that covers much of our Northeast. I mean, it covers places where we typically see our boiler chiller combination. We would typically think, south of Mason-Dixon line, we'll use heat pumps down there. And we don't always think about, northern climates are now absolutely capable of doing that. And when we think about the cost of operation for having a chiller as well as having a boiler and the maintenance that goes along with it and the carbon emissions that we're utilizing because the majority of the time we're using it in heating applications up north. If we start looking at that heat pump solution, we're now actually removing 2 plants, putting in a common plant that serves our needs with 1 new appliance. What kind of tonnages are we talking about with these new heat pumps?
Yeah, so they come in 35-ton modules.
Okay.
And they have compressors that are variable speed.
Oh,
so
yeah.
a lot of turn down.
Betcha.
And we put them together in 1, 2, 3, or 4
modules. Okay.
And if you want more than that, we have partners that'll put a lot more than that together.
Oh, really?
So yeah, sky's the limit. I forget what the limit is, Rob, on how many modules it can work as a system.
30
controlling something like
put
that.
together.
It's a lot times 35. Yeah, that's a lot of
It's not only
tonnage.
practical to do that in
Yeah.
one system, but you can control it as a 32 unit array.
Sure, absolutely. All right, so now we can go from these large inefficient plants down into these nice modular plants. And so you're mentioning, so we're using variable capacity control, even on, say, a 35-ton system, that we're going to be able to modulate down. That 35 could cover anything from, I would assume, like 10 to 35 tons, somewhere in that ballpark.
Yeah.
And so we have less SKUs that we got to worry about. And so we have the potential of having a significant amount of capacity out of one system that we can modulate down versus typically our gas-fired appliances. We're going to be cycling 100% capacity. We're going to be having less efficient heat transfer in many different places along the way versus using a heat pump technology that is now allowing us to modulate using less electricity and energy when we need to.
That's right.
So the transition to really, we're talking about a modulating inverter for conditioning water.
That sounds accurate.
I hadn't thought of it that way, but I think that's
Yeah,
the way to describe it.
absolutely. We talk about inverter technology, right? Everyone loves
Putting them
inverters.
together. I like that.
Yeah. And so it's a solution that not everyone thinks about.
That's right.
And so if we start thinking about the applications, then it's a matter of starting to change a mindset, right? Starting to show that it actually works. So do we have any examples of where we have actually integrated this into existing hydronic systems
Yeah, absolutely.
in the performance?
Yeah, so what you have to look at is what was the original design temperature for all the heating coils in the building.
Oh, yeah,
right?
sure,
So
for the load condition of the space,
you
yeah.
look at that. So yeah, and can you get close enough to that that the system's going to work?
Right,
So if you were designed for 140, you might be able to get away with 130.
okay.
You need to probably do a little test where you might turn down your existing equipment to that 130 degrees and see if there are any spaces that get out of control during
Right.
winter. So that would be easy to determine.
Yeah.
You might have to replace 1 or 2 heating coils,
Right.
maybe. Being able to do that 130 to 140 gets you right in that range that you can match up with a condensing boiler system. Now, the other thing is almost every building today, you hear about 2-pipe and 4-pipe.
Yes.
So a 2-pipe heat pump, a reversible heat pump, either makes hot water or chilled water.
One or the other.
Right, one or the other. And from a building perspective, there aren't too many buildings left that have a true 2-pipe system, right? The old dormitory might, at an older college might, or something
Exactly.
like
Just switch between seasons, and that was it. It was just a matter of getting some conditioning at some times through the year, not consistent across the line.
that. Exactly.
Right.
So we always want to design our systems with hot water and chilled water for the control that we need at different zones and so forth. So that's what the building's going to be designed for. In a 2-pipe air source heat pump, you can install those, and with a very complicated valving arrangement, you can accommodate serving a 4-pipe building where some modules are making chilled water, some are making hot water, but they can only pull the heat from the ambient air to make that hot water. And when they're in cooling mode, they reject the heat through their condenser coils. The difference in the YMAE is it's a 4-pipe air source heat pump that also has water-to-water capability. So meaning that it can take the heat out of the chill water loop, and doing nothing with the condenser on top of the unit, it will create the hot water with that
transfer.
heat. And that's where Rob's talking about that single electrical input that gets you the two beneficial outputs, right? The chill water you
Right.
needed and the hot water you needed from one input of electricity. So that's why you get such a high combined COP.
Well, yeah, because now we're talking about a heat recovery system. If we were
Yes.
comparing it to like a refrigerant cycle system,
Correct.
where we're just simply moving the heat that we've removed from a space and putting it into another place without rejecting it to
Right.
the outside. Very nice technology, but can be very expensive and doesn't always fit our retrofit applications.
Right.
So in a retrofit scenario, we're simply just replacing the means of conditioning that water. And that's all we're actually doing.
Well, in Clifton, we're
Very used to systems that we separated that.
Yeah.
The boiler does hot water, the chiller
This does heat, this does cool.
Cooling, and never the two meet.
No.
Right. But when we come back to our goal is, and where we're going to get the efficiency and
Yeah.
the decarbonization is moving that heat around. We want to keep the heat in the building.
Yeah, exactly. We don't
Right.
want to lose it.
Right. So if I need it somewhere else, let's take it. If we've got to boost it, right, and
Right.
send it to another place where we can use that heat. And there's lots of those applications. We talked about that at the beginning,
Right.
in a commercial building, right?
Yeah. So I'm sitting here thinking about, okay, what if we're moving heat? Say it's in a place we're wanting to move heat out of a structure,
Yep.
and a lot of times we would pull that heat out, we'd reject it to the outside.
Yep.
Well, could I use any of that for domestic conditioning?
Absolutely. Yeah. I mean, you think about the domestic load, right?
Yeah.
Let's say it's typically not any higher than 140,
Right.
Right. And in some applications, coming back to, I'll give you a nod to some residential.
Yeah.
It could be less than that.
Yeah, absolutely.
Right? So I can use that to make domestic hot water,
Oh,
right?
my
That's
goodness.
just another load of heat
Yeah.
that I can use energy and move it around to be able to repurpose it.
Yeah, especially on some of these larger structures. And I take this facility right here.
Correct.
Yeah.
Yeah.
If I want to move the heat from this building, do I really want to reject it outside and then run another system that's actually going to put heat into the water?
No, the last thing you want to do, and that's the beauty of all of these conversations we're having around decarbonization,
Right.
is that as engineers, we are starting to think differently about the energy.
Yeah, absolutely.
And the last thing we want to do is throw it away.
Exactly.
Only if I can't use it for something
Put it
else
to
do
use
I want
somewhere.
to send it out to a cooling tower, or reject it out of the building, or exhaust it. Right.
Right.
But
Yeah. So one of the other things that we were talking about earlier that's a little bit hard to get your head around is the concept of turning off your air side economizer. Because if you're using air side economizer, you're going to be exhausting more heat from the building.
Absolutely, you are.
So
You're
if
right.
your ambient air temperature is cold
All right.
and you need to make hot water, if you can use the warmer chilled water at a temperature that's lower lift for that compressor to work against, it's going to be more efficient than extracting the heat from the cold ambient air. So there are many conditions where it actually is advantageous to shut off your air side economizer, keep that heat in the building,
Right.
so that your heat pump, your water-to-water capable heat pump can take advantage of that to hit a higher COP than it would if it was just extracting the heat from the ambient air.
That's crazy to think about, something so simple that we can take and just really control energy and focus on, like, what are we doing with energy? It's energy. We can
Right.
transfer it to a variety of different means, through
Correct.
air, through water, whatever,
Yeah.
through solids.
Yeah.
So if we change our mindset, and it will take a mindset change
Sure.
to look at any kind of structure and go, okay, where's my energy coming from? What energy am I not wanting to have in this place, and where can I put it where it's most useful?
And that second part is the key, Clifton. It's a lot of times we might say, okay, I don't need this here.
Yeah.
Let's get rid of it. Now you're saying, where else can I put it?
Yeah, exactly.
That's the big difference.
I mean, I think about, like, so many applications. It's they take a multi-story hotel, and we have in the summertime, maybe it's into the evening, we have all this heat from all of our occupants.
Correct.
Normally we would pull that heat out of the building and
Yep.
we'd dump it outside.
Yep.
If they wanted to go swimming, well, we'd have to turn on our gas-fired heater to actually warm up the water in that swimming pool for
Yep.
them to enjoy inside or outside.
Right.
Now I can actually just take the heat that was in those occupied spaces, remove it, make them more comfortable, send that heat to places that they want to enjoy it, like
Correct.
in conditioned water for domestic
Right.
hot shower,
Correct.
in that swimming pool,
Yep.
hot tub, wherever they actually want to use it. And
Yeah.
then if it needs to be raised, you can use some kind of a supplemental heating device to get it to a higher temperature if we need it.
Correct.
But sounds like most of the time we're actually not even going to need to do that.
Probably
No.
not. Yeah.
Yeah.
Wow.
In most cases, you wouldn't.
Yeah,
So,
exactly.
yeah.
Think about 100 degrees or so for even a hot tub. So I can
Correct.
actually supply heat to my hot tub through energy that I
Right.
removed from me.
Right.
Yep.
Now explain that to somebody who's staying in that hotel.
Yeah.
Right. The heat, the cooling we're doing in your room
Right.
is warming the hot tub you're going to sit in later.
I would stay at
Right.
that hotel.
You would stay at that
If
hotel.
you presented it differently, if you said,
yeah.
I will take the heat from you and I will put it in a place that you want it, and we're not going to use energy to do that.
How
And-
about that?
And
Yeah.
I'm going to go, that's where I'm
And are you
staying.
going to lower my bill to do that too? Well, that's another topic.
That's right.
Okay.
That's another
Okay.
topic.
Okay.
But just the thought of, when we look at that decarbonization and that ability to conserve the energy that we are using, right?
Yep.
You can call it whatever you want it. I'm going to call it being efficient with
Sure.
the energy that I consume. So I know that I'm going to be using energy. And if I can reduce what that energy costs for me to use, man.
Absolutely.
And so then we multiply that onto a structure and multiply that into any type of environment where we have places that needs heat transferred.
Yep.
It's kind of endless when we start thinking about the solutions that it can provide.
Yep. Another great example is a hospital.
Okay.
Almost always in a hospital, you have a need for chilled water cooling and hot water heating
bet.
every day of the year.
Yeah.
Right. So, and you're running a chiller in the middle of the winter, and you're dumping that heat over a cooling tower.
Yeah,
And
releasing it.
you're running a boiler, burning natural gas to create
Yeah.
that hot water that you need.
Yeah.
So a water to water heat pump in that case can take care of all the chilled water load in the winter that's present and take all that very low grade, not super useful heat
Yeah.
and raise it to a useful temperature that it can be put into the heating system. And that takes load off the boilers and saves natural gas.
And for those that aren't aware, when we talk about this is not just like something that happens on small scale across the country, across the world. We're talking most facilities that you currently use are using dual sources of energy simultaneously, one to extract heat from something and one to add heat to something.
Yeah.
And so we're absolutely using double the energy to do some work that we could eliminate at least half of that. And then if we start using the inverter technology, we start using these higher efficiency products. Now I see where that COP. And so for those of you that aren't familiar with COP, because we're very comfortable talking about coefficient of performance, what we're really talking about is for every 1 watt of electricity that I purchase, how many watts of heat will it produce? And so when we talk about from heat, like every watt is 3.14 BTUs or so. So for every watt of energy that I can save, we start looking at its COP because it's increasing that COP. So every time I increase that coefficient of performance, I'm reducing my cost of moving the heat. The heat load's there. The heat load's not changing.
Right. Yeah.
It's what type of energy are we going to use to make that transfer happen?
And that's right. And when you talk about the COP, with a gas-fired boiler, it's anywhere from 0.8 to
That's
maybe
horrible.
0.9.
Yeah.
And then with an electric boiler, it's 1.0.
If we're lucky.
Yep. And then if you look at an air to water heat pump, you're talking about something in the probably 2 to 3 range as far as the COP, extracting the heat from the air to
Right.
create the hot water. But for any bit of that simultaneous heating and cooling load, it's
increasing
COP
that
at 6 to
COP.
8.
Yeah.
That's a combined COP.
That's something to get excited about. Right?
That is. So, I mean, if we think about it, like if I was using any type of electric heat and electric cooling, whatever those means are,
Yeah.
and I'm paying, if I'm paying, 13 cents for whatever, right?
Yeah.
I'm paying some price.
Yeah.
I'm going to pay this price for it. Like, how much work is it doing for me? And when I rethink the process, I can like double the work that it was doing by just moving it.
Correct. Yeah. Well, that, and again, I'll come back to a statement we've said a couple times.
Yeah.
Right. One electrical input
Yeah.
doing
How?
2 functions. Right.
Yeah.
Getting more out of whatever I paid for. So,
Yeah. Well, think about that. I mean, when we're talking about that COP of the equipment,
Yeah.
right? Yeah, we were running like if we had electric and we had gas, like that's not like 1 to 1 and 1 to 1 equals 1 to 1.
Right.
That's now 1 to 1/2. Right?
Correct.
Because
Yep.
for every excess energy that we're using from a source,
Right.
if we can reduce that back to one energy input versus those multiple energy inputs, well, that's solving a lot of problems.
Yeah, it is. And you think about it too. So the other thing you have going against you,
Yeah.
operating costs.
Yeah. Yeah.
In a lot of places, natural gas is very inexpensive,
Right.
right? Relative to the electric.
Sure.
So you need that multiplier of the heat pump to make that
To make up the
more
difference.
cost effective,
Yeah.
because I might want to decarbonize my world, but how much am I willing to pay to do it?
Yeah. Oh, absolutely.
Right.
Yeah.
And how much are you going to have to twist my arm and force me to do it
Yeah.
and regulate me to do it versus, hey, I want to be able to do it. And oh, by the way, it's good for my operating expenses.
Massive.
So,
And then we think about, when I was thinking about capacity, I'm like, all right, so we're just building, 30-ton units, 100-ton units, 250-ton. When we start thinking about that from a modular aspect, now we're really looking into redundancy. Like if I have one chiller plant and if I have coils that freeze up, something happens where I
Right.
lose capacity from my one system.
Yep.
I've lost 100% capacity versus that modular design. Even if I had some type of a failure of one of my modules, I still have capability up to however much I'd lost.
Correct.
So we're actually using heat pumps to create redundant heating and cooling systems within what used to be a go no go scenario.
well, because part of that is, Clifton, you can do that relatively inexpensively.
Yeah.
Right. I can add a couple more modules
Yeah.
and get some redundancy instead of 2x of something.
Yeah.
Right. Or 3x
Yeah.
of something.
What about we
right?
just
So,
expanded the building?
yeah, exactly.
Now my
Just gonna add
existing
on.
power plants are not even capable if I was in a
Right.
chilled system and a gas system.
Right.
I would have to upgrade both of those systems to accommodate my new load versus, we add a module and some extra piping.
Exactly.
Yeah.
Exactly.
Boy,
Yeah.
that's
Yep.
getting ahead of the game.
Yeah, it is.
But it takes a mindset.
We have to think differently.
Yeah.
Right. Again, we're thinking differently about what we're doing with the energy.
Yeah.
Now we have to think about how we're going to make that work in the system. And the heat pump gives us an opportunity to do that,
Yeah.
right? From a standpoint of a technology
Right.
that can take care of all those things if we take the time to understand enough about that and how that
How it
has to
works.
adapt to the system. And I'll go back to John's comment.
Uh-huh.
Yet we get to keep a good part of the system where we're comfortable from a design standpoint. We're comfortable with chilled water, comfortable with hot water, comfortable with 4-pipe, right?
Mhm.
So it's not all new variables, right? So
Yeah. And one key point,
Yeah.
if you're going from an air-cooled chiller and condensing boiler system to an all-electric, decarbonized, no Scope 1 carbon emissions system, right? And if you're on a 2-pipe air source heat pump, you might get a little bit of operating cost savings. Okay, your natural gas being
Yeah.
inexpensive, you're going to be getting a COP of 2 to 3, somewhere in that range.
Sure.
But the way that you can start moving into a faster payback, a more significant OPEX cost savings, is by having that water to water capability, right? As many hours in the shoulder months, you have a lot of simultaneous heating and cooling going on.
Yeah, absolutely.
There's an opportunity to improve that average system COP that a 2-pipe air source system does not give you. So if you want to break even or do a little better and you're okay with that, then the 2-pipe is an okay approach.
Still an improvement.
It's
Yeah.
right. But if you really want to capture that energy savings and take advantage of that really high COP operation.
Could you imagine when you're looking at that difference between a 2-pipe upgrade and a 4-pipe upgrade, jumping from a 2 to 3 COP to a potentially 6 COP, and then we look at that from utility costs? Could you imagine cutting the energy cost of this building in half? That's the
Tremendous.
potential. When we go from a 3 COP to a 6 COP,
Yeah.
Yep.
we have that potential.
yeah, and then we have to think about it on that scale, right? Because that's what helps fund it,
Yeah, exactly.
right? Again, I may want to decarbonize. It might feel like the right thing to do,
Right.
but am I going to spend more money doing it?
Yeah.
Yeah. So you talk about mindset changes. Rob and I, when we've really gotten deep into this, we start thinking about where are those simultaneous heating and cooling opportunities. Those are really the lowest hanging fruit,
Yeah.
right? So if you can think about, you have a manufacturing facility that has process cooling needs year round.
Yes,
right?
absolutely.
If you were designing one from scratch, greenfield construction manufacturing facility, you'd be crazy not to use your process cooling heat source to heat your building.
Relocate it back into the
You could
structure.
And if you're talking about that, you could design your heating coils for 110 degrees or something really low like that. You might have 4-row coils for your heating coils.
Right.
But if you start with that design temp, you can apply even conventional centrifugal chillers that are capable of making that 110 when you need it in the wintertime and capturing that. And then they can, with variable speed drives, dial back in to just operate as regular chillers without any real penalty during the summertime. So it actually turns out to be what I would say is the lowest first cost approach as well, because you could dual purpose all the chillers in that chiller plant as heat pumps and conventional chillers. They're going to provide your wintertime heat by pulling the heat out of your process load that you needed to cool with chilled water.
Absolutely.
Same thing. And in those cases, with that kind of low temperature and that compressor technology, the COPs can be in the 10 range.
No kidding.
Or something like that.
Yeah, so on that capacity, it really changes an operating cost from a facility drastically. All right, so what are some ways, we've got a few minutes left, what are some ways that people can learn about this? Like, how can we learn more about connecting with Johnson Controls and thinking outside of our mind, understanding that there are solutions available to you? Where do I begin?
Well, part of it will be listening to this podcast, right? So I have to promote that for you, right? But
there you go, right here.
even within our own organization, right? We have lots of educational opportunities, right? I think about folks that work in John's territory, for example, as an area manager. Our salespeople are tremendous resources, right? To be able to help educate customers. And then layered behind that, we've got all sorts of resources that you could self-absorb, or hey, we'll just bring in experts and talk to you about your projects. So
that's your scenario.
Exactly. Yeah.
So I encourage everyone to connect with Johnson Controls, learn more about new ways and new perspectives to accomplish our decarbonization goals. Thank you, gentlemen.
Thank you.
Thank you, Clifton.
Absolutely.